Hi everyone, this is Chen from PUC-Rio. Today I would like to share with you my recent work on this issue of the quantum geometrical properties of topological materials. So in essence, what I want to show you here is that starting from the quantum metric of these topological materials described by the Dirac Hamiltonians, you can extract a bunch of geometrical properties as defined in the usual textbook of differential geometry. And nevertheless, this very simple exercise reveals a lot of very interesting properties of the momentum space of the Dirac Hamiltonian. So it goes like this. So in the previous video, I have already shown you how this quantum metric is defined. So basically, you started from some gap materials where you have some number of field valence band states or the field quasi-Hall states if you are a superconductor. And because they are fermions, so you need to construct this kind of fully anti-symmetric valence band state, the Slater determinant, where each one is each individual valence band state. Now, this is defined as specific momentum, right? So if you take two of such states at slightly different momentum and make a dot product between them, calculate their overlap, then do an expansion on this small momentum difference, then you will see that the leading order correction is quadratic in this small displacement of momentum. And the coefficient in the front is what we call the quantum metric. Now, the quantum metric, as you can imagine, it is gonna be some Taylor expansion of this original state, right? So for instance, its diagonal elements will look like this. Now, I like to think of this quantum metric as it describes how the state that you have, this valence band state, as a unit vector in the momentum space, it will point in some direction in the Hilbert space. And when you move from momentum k to k plus delta k, then it's going to rotate into some different direction, right? So you're basically calculating the product of these two unit vectors and do expansion. So it's like product of cosine, the leading order is quadratic. Now, particularly for Dirac models, which are relevant to topological insulators and topological superconductors, where your Hamiltonian is described by a D vector that describes the momentum dependence of the Hamiltonian product with the gamma matrices, the Dirac matrices. Then if you construct a unit vector, that's the D vector divided by its module, then you can easily show that the quantum metric is actually given by the product of the derivative of momentum of these unit vectors product with itself. Yeah, so this gives a very nice interpretation of the Vierbein in differential geometry, as I have shown you in the previous video. So now the idea is once you have this metric defined, let us calculate some differential geometry out of it. Yeah. So a very good reference of all the formula that I'm going to show you here is Sean Carroll's book about space-time and geometry, which is an introduction to general relativity. And so you go to the usual procedure. So for instance, the first quantity that you can define out of a metric is a so-called affine connection or the Christopher symbol. Yeah, so you take a derivative on the metric if your metric depends on momentum, and then product with the inverse of the metric. Then you can construct a tensor that has three indices. Now, out of this affine connection, an important quantity that you can address is the geodesic, namely, from point A to point B. Let's suppose you're wanting to go from point A to point B in momentum space. Yeah. And you are trying to find the shortest distance between them. Then this shortest distance has actually a very interesting interpretation in terms of this quantum metric and this fully anti-symmetric valence band state. It goes like the following. You imagine that at each point you can assign a Hilbert space because each point defines a quantum state, right? And so the quantum state is like a unit vector at every point in the Hilbert space. But as you move from Ka to Kb, this unit vector keeps rotating in the Hilbert space. So geodesic is essentially the trajectory along which this rotation in the Hilbert space is the least. Yeah. So this gives you a very nice interpretation of this geodesic in terms of the overlap, because you're trying to minimize the overlap between every neighboring quantum state. Okay, and then from this affine connection, you can also construct the Riemann tensor that is given by its derivative and also the combination of itself in such a way. And then you, from this Riemann tensor, you define the Ricci tensor by contraction, and also multiplying the inverse of the metric, then you can get the Ricci scalar, which essentially characterizes the curvature of your d-dimensional manifold, your d-dimensional Brillouin zone. And then from there, you can proceed to construct the so-called Einstein tensor, which in general relativity enters the Einstein equation, as I will show you in a minute. And also, differential geometry has an interesting property, namely, if your Riemann tensor, the one with all indices, all lower indices, and the metric satisfies this relation, then the space is called the maximally symmetric space, meaning that your metric has the maximum possible symmetry that you can have on this manifold. Yeah. So all this that I'm showing you are standards in any differential geometric textbook. Yeah. So I'm just trying to use, now the idea is to use, okay, what if I use a quantum metric here to begin with? Well, is there some interesting properties I can get out of this standard formula of differential geometry? Now, what I found is that the manifold actually possesses a lot of very interesting properties. First of all, let's fix a model. Let's use a linear Dirac model in 2D. Let's first try 2D. So now the Hamiltonian contains a mass term that determines your topology, and the Fermi velocity times a momentum along x direction, where if you write it in polar coordinate, it looks like this, and the momentum in y direction, which if you really put it in polar coordinates, then it looks like this. Okay, and then you go ahead and calculate quantum metric using the field by formula that I've shown you earlier, and it looks like this. In the polar coordinates, because the model is completely symmetrical with respect to the high symmetry point, right? So it makes more sense to work in the polar coordinate. So this is the metric, and you can also go ahead and calculate a Riemann tensor. It looks like this, and then the Ricci tensor, the usual standard procedure. Yeah. And the geodesic, you just write down each component of the geodesic equation, and then it looks like this. And by the way, the geodesic problem in 2D is exactly the same as the Kepler problem that you're solving in your classical mechanics course. How the Earth orbits around the sun. Yeah, it's really essentially the same equation. Okay, and using this, what I found is that first of all, it turns out that the volume of the Brillouin zone is actually a constant, because the square root of the determinant of the quantum metric is what is called the volume form. And if you integrate it over the entire uh, uh, polar coordinate, then it gives you the volume of the curved Euclidean space. And it turns out that the result is a constant in the sense that it does not depend on the mass turn of the Dirac Hamiltonian. So meaning that whether it's topological and non-topological, the result is the same. Or whether it has a larger Fermi velocity, smaller Fermi velocity, the answer is still the same. Yeah. And secondly, the Ricci scalar is a constant. Moreover, is given by 16 divided by the dimension of the Dirac Hamiltonian. So the dimension of the Dirac Hamiltonian n is determined by the symmetry of the material. For instance, in 2Ds, for some symmetry classes, you need a 2x2 Dirac Hamiltonian to describe your system, whereas in some classes you need a 4x4 Hamiltonian to describe it. So this depends on symmetry. It depends on symmetry, but nevertheless, it is a constant throughout the Brillouin zone. And this point has already been pointed out by Matsura and Rio in 2010. And in addition, the Euler characteristics. So the Euler characteristic in 2D is defined as the uh, integration of the volume form times the Euler characteristics. Right? Since they are all constant, you can see that they multiply together to give you one. And you know the Euler characteristics uh, according to the Gauss-Bonnet theorem, is essentially 1 minus the number of handles or 1 minus the number of holes that a 2D object contains. So this means that these two-dimensional Brillouin zone of the topological materials does not have a hole. So it is somewhat analogous to a simple uh, soccer ball, for instance. So and moreover, it has a constant Ricci scalar, right? So it is really like it is really more like a perfect sphere that has a constant curvature everywhere, and it does not contain any hole. So, and moreover, if you solve this geodesic equation, you found that it is actually a straight line, meaning that anywhere from A to B in the momentum space, the shortest distance is a straight line. However, this straight line is not the usual straight line. So in general relativity, a straight line, for instance, straight line along x direction is x equals to velocity times time. Because it just means that if an object keeps going along a certain direction with increasing time, then its coordinate is going to increase, right? And this is what you usually call a straight line in general relativity. But here it is not. The trajectory is straight, but the velocity, if you imagine that there's a particle that is moving along this trajectory, then it is not moving with the constant velocity, actually. It actually changes, the velocity actually changes in this particularly sort of peculiar kind of a straight line. So it's not the same as the usual straight line, although it does look straight. And then finally, you can see that the Brillouin zone satisfies this what's called a maximally symmetric space because they look like this. Okay, now this is the linear Dirac model. Now we can go to a more realistic models to regularize this on a lattice. Yeah, for instance, 2D you regularize this on the square lattice. Then it becomes the usual lattice model of the Chen insulator. Then and then you can only do this numerically, right? So for instance, here I show you that the metric at 3 different values of the mass term, which will correspond to topologically non-trivial and close to a critical point and the topologically trivial phases. And in each one, I plot the metric along x, metric along y, and the off-diagonal term of the metric. And also here, I plot the volume form. Yeah. So numerically, I found that the Ricci scalar is still a constant. Remarkably, despite you have this very complicated lattice Hamiltonian with all these parameters, it does not matter what parameters you put in. The Ricci scalar is always constant, and the Brillouin zone is still a maximally symmetric space. Okay, now coming to 3D. Yeah, then first and once again I start from the linear Dirac model where the Dirac Hamiltonian is just the mass turn, velocity times kx, velocity times ky, and velocity times kz here. And here it is more reasonable to work in the spherical coordinates because in this for symmetry, right? So the metric in the spherical coordinates it take this form, and the Riemann tensor take this form, and the geodesic will look somewhat more complicated. But once again, these are all standard calculations in differential geometry. And what I found in 3D is also quite interesting. First of all, the volume of the Brillouin zone is once again constant and is once again only determined by the dimension of the Dirac Hamiltonian. And the Ricci scalar is again constant. So once again, this means that your momentum space is sort of uniformly curved everywhere. And remarkably, the Einstein equation is satisfied with a finite cosmological constant that is determined by the dimension of your Dirac Hamiltonian. Yeah. So this is the usual Einstein equation. If you don't have any mass, then the right hand side will be 0. And right, so this is satisfied with a constant cosmological constant. And it turns out that you can simply use a contraction with the inverse of the metric to this equation. Then you will see that the fact that cosmological constant is finite and the fact that the Ricci scalar is constant are basically the same thing. So in other words, one implies the other. Okay, and once again, the Brillouin zone is a maximally symmetric space, and also you still have the straight line geodesic. Yeah. So and then uh, further using a lattice Hamiltonian to demonstrate this. Yeah. So in order to make connection with more realistic 3D materials. So once again, I regularize it on the 3D is the same as the lattice model in 2D, but just generalize it to 3D. And then you do this numerically, you calculate the metric and now which now has three components, right? And here I do it in the Cartesian coordinate. And also the volume form. And then you see that it looks like this. Yeah, so it will depend on whether so the precise shape will depend on whether you are in topologically non-trivial phase or topologically trivial phase. But nevertheless, for all of these cases, once again, the volume of the Brillouin zone is still constant. The Ricci scalar is still a constant. And interestingly, the Einstein equation is still satisfied with a cosmological constant. And once again, despite this complicated form, the Brillouin zone is still a maximally symmetric space. And that's it. So essentially, this is just, as I say, this is just a very simple exercise of differential geometry using this quantum metric. But nevertheless, the consequence is quite interesting. And moreover, many of these properties are completely independent of the parameters of your Dirac-Hamiltonian. Yeah. And that's it. Thanks for watching. And if you have any questions, please don't hesitate to contact me.